I'm very happy to welcome back the Team Mplus. Just to remind you everyone, about a year ago, in March, actually 2017, Bengt and his intensive longitudinal crew did really a series of presentations. I think it was 4 presentations on intensive longitudinal data for PSMG. The team also had several big workshops and presentations outside PSMG, and I could not witness the ones that happened in Europe, but at least I attended a webinar for the American Statistical Association, which was actually one of the best attended webinars. I believe most of us haven't even recovered from last year's groundbreaking presentations by Team Mplus. But here they go again. Today, Bengt and Tiomir will introduce us Mplus version 8.1 and various new features related to intensive longitudinal data, multi-level modeling, and structural recursion modeling. They indeed brought a lot to cover today, and we had some technical difficulties, but I'm glad they got all resolved. So let's get started. Bengt, are you going first?
That's right. Yeah, I go first. So let's get started, folks. And good to be on again. We've been quite busy since we last talked in, March and April last year. And most of the time has been spent on developing methods further for intensive longitudinal data, as you see on the first slide. That has also led to some further developments outside of the intensive longitudinal data, time series modeling area, and actually gotten into more structural equation modeling development. So here we are with the version 8.1, which we hope to release already next week. And what we did since 8.0's release in late April was to give several workshops in the US and in Europe, ending with a 2-day workshop at Johns Hopkins University in August last year. And that got recorded and is now available for you to watch under the short course rubric as topics 12 and 13. Now for this talk, then, I will talk about part 1 and Tiomir part 2. Tiomir will talk about twice as long as I. And part 1 is my attempt at gently leading you into the news of this feature, the new features of the 8.1. I will do that through model figures. Tiomir will talk about formulas mostly. And they connect quite a lot. Tiomir will focus perhaps a little bit more on the regular multi-level modeling than the time series modeling, but he has time at the end for time series modeling as well. I will almost only talk about time series modeling. Now, we focus on modeling issues, so very little applications. You see the applications in these short courses, but we're going to talk about ideas for modeling, so modeling principles, the new modeling opportunities. That's what we're going to focus on. So, Tiomir, if you can move to slide number 2, since I can't move my slides.
Okay, yep, I'm there.
Good. Then we have the time series specific developments listed on that page, and you see that it's chock full, and still that's about only half of the developments in 8.1. Somebody said that it should be more than just 1/10 of a new version. It is really version 9 in some ways. But anyway, so we say that under the first bullet, there are lots of further developments for time series analysis in the so-called dynamic structural equation modeling area, with a focus on RDSEM, our term for residual dynamic structural equation modeling, where the autoregression is between residuals instead of between outcomes. And I'll be more specific about that as we look at some figures. That's the big news, and that's taking quite a long time for Tiomir to develop new statistics and new Bayesian algorithms tailor-made for the various latent variable and SEM models that Mplus offers. In addition to that, we've developed new features for categorical variables. So in this version 8.1, for the first time, we allow lagged relationships between categorical variables. And I'll show you how useful that becomes towards the end of my presentation. Furthermore, with categorical outcomes, we now allow for random slopes for a categorical predictor with latent centering, which is a concept that Tiermer will spend quite a lot of time talking about. And that's in the area, all of this categorical news is in the area of DSEM, not yet for the residual DSEM, but it is also available for regular two-level analysis outside of the time series intensive longitudinal data area. The key reference for this is this Asparuh-Haumacher-Mutén paper 2018, which appeared in the SEM journal. That covered mostly, focused first on DSEM, but also included RDSEM, even though there was no software generally or available yet for it. So here's the software coming a little bit later for that part of it. A source of inspiration here has been the interaction with Niall Bolger and J.P. Lorenzo and their book, where they talk a lot about models that can be classified in the RDSEM category, more so perhaps than in the DSEM category. And I'll show you what I mean by that. The new examples that we can do with RDSEM and the contrast between them and the DSEM examples are described in the Asparuh-Haumacher-Mutén 2018A paper, and you have all the papers listed at the last page of this presentation. And they will be posted sometime early next week for you to look at. The new theory is in a key paper. It's a major paper that Tiermer has taken the lead on and gets most of the credit for, namely a paper on this centered latent variable centering. And that paper also describes the RDSEM part. Now, if you're totally new to this area, you may want to look at our special web page. If you look at the left margin of the home page of the Mplus website, you see a page devoted to time series analysis, where we give a lot of references, theoretical and applied, and training material of all kinds. So with that, let's look at slide 3 and talk about the other developments outside of the time series area. And the first bullet there on slide 3 is the multi-level modeling area. And that is what Tiermer will talk about almost exclusively in part 2. So he'll talk about random slopes with latent variable centering for predictors. The predictors that have random slopes and are latent variable centered as opposed to observed variable centered. And that's for DSEM, for RDSEM, and general multi-level modeling. But we also have some news for structural equation modeling, which I think are really interesting. Particularly this first bullet, the automatic checking of whether two models are nested. It's an idea by Peter Bentley and Albert Satora that came out in Psychological Methods in 2010 and wasn't really visible. I don't think it was ever implemented in commercial software. I think it was an R program that could be hooked up to Bentley's program. But what we've done is put it into Mplus, make it easy to use, generalizing it to multiple group situations and categorical and censored outcomes in the weighted least squares estimator context. And we found it quite useful, and Tiermer has taken the lead on writing a paper on that, which describes how very complicated algebraic proofs of nesting can be replaced by, or at least complemented by, this simple two-step run in Mplus 8.1. Very useful and interesting story. And Tiermer has also gone through and developed the root mean square residual fit index for new situations. We've sort of redefined it a little bit. We'll see how people react to that. and made it available also for the weighted least squares estimator, and made changes also for multi-level and models with covariates. In addition, there is some extra things with for the weighted least squares bivariate residual test for the first time, and standard errors for factor scores for the first time. Added some 2 levels cluster-specific plots and some more odds ratio output that users have asked for. Okay, slide 4 then. There is the distinction that I make between DSEM and RDSEM, the way I look at it. So 2 typical examples. First of all, within the DSEM category, on slide 4, there's a paper by Ellen Hammacher, for instance, who's written on daily measurements of negative and positive affect over 100 days, so intensive longitudinal data, where the focus is on the autoregressive parameter in the regression of y sub t on y sub t minus 1. So y, the outcome at one time point regressed on 1 or more earlier time points. And the autoregressive parameter in itself is the focus, because it has a substantive interpretation, like expressed here, how quickly a person restores equilibrium after being perturbed, interpreted as inertia. And it's interesting to study how that parameter varies across individuals, across subjects. It becomes a so-called random effect that varies across individuals. And you can look at antecedents and consequences of that random effect on level 2, on the subject level. For instance, differences across gender and differences in various kinds of outcomes. Now, in RDSEM, on the other hand, the focus is a little bit different. If you take the example, a very good article by Liu and West, daily diary study over 60 days. It had to do with, the example was stress during the day influencing alcohol consumption that same evening. So the focus is more a regression of YT on XT. So Y on X at the same time point. Sure, there is autocorrelation across time because the time points are very closely spaced over time. The measurements are closely spaced. But that sort of becomes a residual interest. The focus is really on the contemporaneous relationship between Y and X. Now, if you show that in pictures, you have slide 5, where at the top you have the DSEM situation, where YT is regressed on YT minus 1. True, we have Y also regressed on X as a covariate, but perhaps the critical part is the phi, the autocorrelation coefficient between YT and YT minus 1. And the contrast then RDSEM at the bottom, where the relationship between over time is captured by the residual of YT being regressed on the residual of YT minus 1. And the focus is really on the contemporaneous regression of YT on XT. So there's a difference. And this kind of analysis you can do for a single subject. Just have to have many time points, maybe 50 or so. So this is an n equals 1 situation. What we're missing here is the multi-level aspect. That is the multi-level time series aspect, which is shown on slide 6. So on slide 6 at the top, you have the relationship between Y and X, which is the focus, and you take into account autocorrelation in the residual of YT, regressed on the residual of YT minus 1. And now we pay attention to these fill circles. So for instance, YT regressed on XT has a filled circle at the bottom of the YT box. That's a random intercept. And a filled circle on the arrow from X to Y. That's the random slope S. And then we have the autocorrelation at the top, R, I call it, for the residual. That's also a random effect that varies across subjects. And then the residual variance in that regression of the residual on another residual can vary across subjects as well. So all of those filled circles at the top become open circles at the bottom, namely continuous latent variables on the between level, between being the subject level in this case. And because it is a subject level, we will have many such random effects that have significant variation, whereas in other multi-level contexts, you have relatively few when the between level is, say, classroom and or school. And the picture at the bottom shows an observed between level variable covariate W that influences the random effects, and you can also let the random effects influence another observed variable, distal outcome of some sort. Actually, you can have any kind of structural equation model on both within and between. Now, if you really want to see what's going on here, and as an intro to what Tirma is going to talk about, slide 7 shows what's really going on, what's really being done. And this way of depicting the model in more technical detail, I guess I would call it, is credit goes to Ellen Hammacher, who started doing that in our Hopkins training sessions. So on the left, you do a latent variable decomposition of the y and x variables. So for instance, yt is the sum of ytw within plus yb, the between part. The yb varies only across subjects. It would have a subscript j if you brought in subscripts. Same decomposition for x. And then to make the modeling very clear, on the within part, we have the within relationships. All the circles there have superscript w. And the rest is on the between part. So it's latent variables then. It's the latent variable decomposition that we work with. So ytw is regressed on xtw. And still we take into account the autocorrelation across time for both y and for x. And the random effects end up on level 2, where yb and xb, those circles at the, at the bottom of the between part, are essentially the random intercepts, or random means in this case, since we have centered, as Tirma will describe. Excuse me. And then we have the random slope, the random log variance, and the random autocorrelation for y and for x. So that's the full story. So you may want to have that picture in mind if you like pictures when Tirma starts talking about formulas. Now on slide 8, we have the new language for the residual DSEM. On the left, you have the familiar language that is an 8.0, the DSEM for an autoregressive lag 1 model. You have a random slope S bar y on x, so the slope multiplying x there is random, varying across subjects. And then you have phi, the autocorrelation, autoregression of y on itself at the previous time point, y on y ampersand 1. And then if you have missing on x, you may want to add x on x ampersand 1 to bring x into the model. For the RDSIM situation in version 8.1, the regression of y on x is the same, but the autocorrelation part comes in for the residual. So on the second line, we say r bar, r is a random coefficient, y hat, it refers to the residual of y in its regression on x. That residual is regressed on the residual, the same residual at the previous time point, y hat 1. So that's the difference in language, quite simple. And then you can bring in the x's if you want as well. Slide 9 then, if we go a little bit further and go beyond regression to mediation analysis, you have a situation at the top right. You have y regressed on a mediator m and a covariate or a treatment variable x. And you see then that the regression of interest is that mediation model ymx. And we take into account the correlation across time in the residuals for y and for m. And we have a lot of filled circles, a lot of dots in there, which represent where the random effects can be. So here you have a very general situation, which is quite unique. You have a random slope between y and m, so that you have two dependent variables, y and m, and you have a random slope connection between them. And on between, then, you end up with 1, 2, 3, 4, 5, 6, 7, 8, 9 random effects. And you can imagine trying to do that in maximum likelihood is hopeless with high dimensional numerical integration. And again, those random effects can be predictors of some other variables. Now, when it comes to mediation in longitudinal data and time series data, it's a very difficult topic to handle correctly. There may be lagged effects that should be taken into account. Very difficult area to deal with from a sort of causal inference point of view. And we were reminded of that by a brand new paper, which is mentioned at the bottom, in Multivariate Behavioral Research that just came out, cross-sectional analysis of longitudinal mediation processes, that I urge you all to read. Excuse me. That is one of several papers that deal with mediation in longitudinal settings. More papers are in the pipeline. It's an interesting topic. I just showed the model from the point of view of easily generating a lot of random effects. So if you go to slide 10 then instead, we get into factor analysis. So at the top, we have a new kind of factor analysis model, which I think was inspired Tiermer and I by Phil Wood. So what you have is a factor analysis. If you look at the time point t, that is top right, you have three indicators of one factor regressed on one x. That's a model you're interested in. Now you just want to take into account that you have closely spaced measurements over time, and you're likely to have strong autocorrelation across time. So you do the autocorrelation for the residual of the factor and for the residuals of the factor indicators. So instead of having a regression of y1t on y1t minus 1, so the direct regression of the indicators on each other, you do the regression among the residuals. You separate the residuals in the observed variables from the residuals in the factor. So you have two orthogonal parts there, easier to interpret when you separate it out that way. And the model has then random intercepts for the y's. Those are the filled circles at the bottom of the boxes, top right. And you have a random slope for f, excuse me, a regression on x. And you have random autoregression and random residual variance. So that's showed at the bottom. At the bottom left, then you can actually put a factor on between FB, which is measured by, indicated by the random intercepts, the latent continuous variables, y1 to y3. And then you have the other random effects, S log V and R. And you have an observed variable, just as an example, W, that influences both sets. Now, so that's one more set of showing the general SEM type of variable framework that all of this time series analysis of intensive longitudinal data, all those analyses are embedded in that general SEM framework for both within and between. Going one step further on slide 11, you have a familiar picture where you show growth modeling or trend modeling over 5 time points, y1 through y5, and you have growth factors in random intercept, random slope, I and S. You have a time invariant covariate W. You have 5 time varying covariates X, 1 through X5. And this is then drawn in a single level wide format, adding autocorrelated residuals. So on top of the Y's are correlated not only because they're influenced by the same growth factors, I and S, but they're correlated also beyond that due to other say unobserved covariates that influence Y at the different time points. And again, it's not a direct regression between, say, Y2 and Y1, but between the residuals of Y2 and Y1. So you keep the influence from the growth factors orthogonal to the influence from the residuals. I like that way of looking at the model. So now this doesn't work for intensive longitudinal data. It's totally impractical when we go from 5 time points to, say, 50 or a couple of hundred. So instead, then, the solution is, of course, then to go to 2-level modeling, where time is level 1 and subject is level 2. So if you go to slide 12, that is the counterpart in time series analysis of ILD. It's the RD-SEM version that translates that previous figure directly into the time series setting, because the residual the autocorrelation sits at the residual for YT, and there's no direct regression between YT and YT minus 1. So therefore, the random slope, S, top right, Y on time, that's the random slope, that's the slope growth factor, has the same interpretation as it does on the previous slide. And again, then you have several random effects in there. Now, that's a quite useful model for looking at trends in time series data. And I have used it for a smoking study where you talk about smoking urge decreasing over time. Now, with categorical variables on slide 13, some interesting developments there too. We have a lag categorical variable. We usually denote them by U, rest on a previous UT minus 1. So we're looking at the DSEM situation here, not the RDSEM situation. So the second bullet then says that we can also have a random slope for a categorical predictor rather than outcome with latent centering that Tierman's going to talk about. That's available for DSEM, not yet available for RDSEM, but it is available for regular 2-level, as Tierman will explain. On slide 14, you have a very nice application area of categorical DSEM because it gives us a way to handle variables with very strong floor effects, which we see quite often in the real data. Say negative affect, for instance, strong floor effect. Here is for the smoking urge data that I've been working on. The smoking cessation study, overall 42% of the floor value. And more importantly, early in the study, after they trying to quit, 27% of the floor value, and late in the study, 47% of the floor value, where the floor value being the value where they feel no smoking urge. So there's a move of observation subjects from the high categories of high smoking urge down to having no smoking urge. And so it's a shift into that 0 category. And for those kinds of variables, we know that, looking at slide 15, 2-part modeling is one quite effective technique that we have used in PCB settings too for growth models. So you transform the variable with the strong floor effect into 2 variables, binary U and a continuous Y. So U equals 0 if you're at the floor, and Y is then designated as missing. You don't have any continuous tail value for Y. And U equals 1 if the observation is not at the floor, and then Y is observed. You do a probit model for U and a log normal model for Y. So that's you get then much more information. You get separate predictors perhaps for being at the floor, for having no smoking urge at all, as opposed to predictors for having a positive smoking urge value. And in picture form on slide 16, you see then the 2-part DSEM regression modeling. You have Y at the top and U at the bottom. So continuous Y at the top, binary U at the bottom, the 2 processes. In the middle, in this case, we just have a covariate X that influences both processes, both the Y and the U, and with all these possible random effects. And then, as I said at the bottom, that 2-part trend growth modeling can then be done in line with Mplus Users Guide Example 6.16. So I'll stop there on slide 17, and I'll let Tiermer take over and go into part 2.
Okay, so I'll talk about centering predictor and mediator variables in multi-level and time series models. Most of this will be regarding multi-level models. There will be some applications for time series models, but at this point, I think we are sort of hell-bent to actually change multi-level modeling. And I hope that in 10 years from now, we get some significant percentage of applications in multi-level modeling to be based on latent centering. I kind of, I'm not sure I'm going to be able to get to my last slide. So I'll just go right now to the last slide. So here's the summary. So this latent centering that we've adopted now for version 8.1 solves many problems. Separation of the level of the effects. It solves Nikel's bias, Lütke's bias, missing data's bias, link function-related bias. It's more accurate in terms of mean squared error, and it's much simpler to interpret. So this is going to be the conclusion. We kind of run into this almost accidentally a little bit. We knew that there was a big issue there that we need to eventually tackle, but almost accidentally run into this. So just a little overview of what's going to happen here. I'm just going to talk about the 5 different types of centerings of predictors in multi-level models. I'm going to give you some 2-level regression simulation examples. We're going to talk about contextual effects, Lütke's bias with fixed slopes, random slopes, probit regression, and binary mediators. Then we're going to bring in a little bit of time series analysis for categorical variables and random tetrachloric autocorrelations, and we'll talk about Lütke's bias. I want to also touch in a little bit about 2-level mediations and the problems that can occur with centering when you have missing data. So how did we get here? So as you know, in the 1990s, when Bengt was doing the multi-level SEM work, that was basically the condition you start. You separate the within and the between level right off the bat, and that's what latent centering is. You separate the within and the between level, and I treat both these as the between level parts as latent. Then I started working at Mplus in 2000, and we quickly got into the random slope stuff for the covariates, because the multi-level SEM didn't technically have a random slope; it was just for fixed slope. We basically added these capabilities of actually having the random slope on a fixed covariate. A couple of years later, people complained, you don't have the random slope for the dependent variables, and so we added, that version as well. Basically, just not doing nothing essentially, but actually treating it as a regular covariate. So basically doing the uncentered version of the dependent variable. Later on, we started adding these define commands that actually would allow you to do some of this centering stuff on the observed scale, the cluster mean command in the define variable, which makes this very quickly and easily. You can actually do some of the other centering methods. And then in version 8, we kind of also accidentally did some work that was related to this final step we did now in version 8.1. So we did we actually allowed missing data for random slopes on within level covariates. That was like a little piece of the puzzle that I ended up going in there, and it was a little bit funny, a week before, the release of version 8, Bengt ran some model, and you did this just for the within part. Was an interesting comment. That the complaints from Ellen and Bengt were very consistent about you didn't do the full version. So anyway, we had to actually. So the other thing that we actually ended up in version 8 was pushed by Ellen, and it was she thought that was very important for her modeling, is that when you have the lagged predictors, so the predictor of the same variable from a different period, those need to be latent centered. And we did that in version 8. And back in a few years, we actually thought that this issue is never going to be completely fixed, that it's too complex to be and it's too intractable. But we actually we finally did it. So that's I feel very happy about this. And I think the way actually this happened is because of this popularity that 2-level mediation models actually brought in. So those, and they pushed a lot by Preacher and Chris Preacher and others. And what happened is that the models became more and more complex that they're actually using. At the same time, the interpretation, the estimation became too difficult with the existing methods. So now with version 8.1, things will change, and everything will be much simpler and better. So the 5 types of centerings I'm going to discuss: the observed centering, ground pin centering, uncentered, the hybrid method, and the latent centering method, which we're promoting now. Here's what our little framework is. Basically the standard 2-level model. You have a random intercept, you have a dependent variable covariate. In a 2-level model, you get a random intercept and a random slope. And this is what Raudenbusch and Brick in their book recommend. You take the sample mean, you subtract it from the covariate, so you basically you center the covariate. And you take that covariate and you can put it on the between level and predict the intercept, the random intercept, with that additional covariate that you just constructed. And we call this the observed centering. That's what was used in Raudenbusch. And So, this has a lot of unsettled question. Is one of the questions is why do you have to separate these variables? Why do we need to center the x, and why do we treat x and y differently? Why is it treated as a random effect on the between level, and then x is just the sample mean? So here's the first question that's easy to answer is why do you have to separate the effects? If you don't separate the effect, then you just have one predictor. You can estimate the random slope beta 0 just in that random predictor. But you cannot not estimate the two coefficients from the previous model, one on the within level and one on the between level. You had two different predictors, and they're different. Almost always they're different. And you cannot estimate the two. And what you get here with the beta 0 random effect is that the mean of that random effect is an interpretable blend of the two coefficients from the real model here on the previous slide. So that an interpretable blend is approximately like a weighted mixture of the two, where the weights are proportional to the inversely proportional to the precision of the estimation, 1 over the square root of the standard errors. Now, just to bring in the fact that the difference, the fact that you have these two coefficients is very important in many areas, and it's basically the difference between the two is called the contextual effect. And there's a lot of work, especially in education studies by Herbert Marsh. A lot of often it's referred to as the big fish small pond effect, because you have these students that are the best students. They compare the best students in the worst schools versus the worst students in the best schools. And then those two effects become very important. So the next centering method that we're going to consider is the uncentered model. So in this model here, you can actually add the contextual. You can study the contextual effect. All you need to do is basically put in the observed between part of x in that equation. So you can keep the covariate on the within level as the whole thing, but then you can just add the average. And if the slopes, if this slope is actually not random, then the models are equivalent with the observed centering model. If the slope is actually random, then they're not equivalent. What happens is that you get this interaction term in there between this residual of the random slope and the between part of x. And that interaction term is actually, it's a very strange and difficult to interpret, and it also I find it strange also because of the fact that it's added to the random intercept with a fixed slope of 1. And when you're adding interaction terms, generally we don't want to add them with a fixed slope. You want to estimate, you put the interaction term in your model, and you want a separate coefficient to be estimated there in front of the interaction term that will be estimated by the data, and will tell you if that interaction term is useful or not. Instead, this model kind of results in, when you put in the within level, on the within level, the entire variable, on the between level, just the between part, what you're getting is this interaction term with a fixed slope of 1. And multiple papers have tried to tackle this, and they all say this is a very strange thing to interpret. And also the problem with this kind of modeling is that it doesn't separate within and between effects, and they are blended together, so it requires more algebra to actually disentangle them after the model estimation. The ground mean model the ground mean centering is just basically pretty much the same as the uncentered model, except you subtract the total mean of x. It's just subtracting a constant, and almost always you can. This is a reparameterization of the uncentered model, although sometimes it's not very straightforward reparameterization. Now, that's so far so good, but what happens is there's a paper by Lutke that actually showed that, even if you do, separate the within and the between effect, and you try to estimate the contextual effect, you center what Raudenbusch and Brick recommended, you still can estimate the contextual effect, and you're actually getting a bias. And that's called what we call the Lutke's bias. And that bias is this, is beta 1 minus beta 2, where these are the effect on the within level. Remember, we only have two variables here. So this is the effect on the within level, and this is the effect on the between level. That's the mean of the random. Here, in Lutke's article, the situation was about fixed slope. And so this is basically, you still can estimate, you still have to get a bias in the between level effect when you are basing your estimation on observed centering. And the reason we are actually doing that observed centering again is to use this sort of old framework of HLM modeling, where we want this the covariate is treated as a fixed covariate rather than another variable. So anyway, so this is the bias that you're getting with beta 2, and ICC here is the interclass correlation for the covariate, and is the cluster size, and these are the two estimates. And basically, so you can see from this formula that if there is a contextual effect, beta 1 and beta 2 are different, then you have bias. If there's no contextual effect, there's no bias. And basically, also you can see that if the cluster size is increased, then the bias actually goes down to 0. But there's another point that you can see here is that regardless of what happens about the contextual effect and the end here, if the ICC goes to 0, then the bias actually increases. So it's a little slightly, not very easy to always know what exactly that bias is. Lütke also showed that latent centering resolves this bias. This is based on the SEM methodology estimation. So here's what the latent centering basically is. It takes the covariate and it decomposes it as a within and between, just like you do for the Y variable in SEM models, and that basically mean is treated as a latent variable. And basically this Lütke's bias does appear because you are having an error in the, so basically the bias appears because this average X bar is a measurement of the mean, and that measurement has an error, but that error is not accounted for. So basically, this is the advantage of this latent covariate modeling framework, that it treats, this is going to be treated as a latent variable that is being measured by these x's, and that's a proper framework to handle the measurement error. And in terms of SEM language, we basically use, you can write this slightly differently than in HLM. In HLM, you basically have a random intercept and then a slope. Here, in the same framework, we usually try to decompose the dependent variable as a within and between, and then basically have Y within on X within on the within level, and then Y between on X between on the between level. So that's the SEM version of this model, but it's the same model, of course. So here's let's go to the hybrid method now. The hybrid method, you can estimate Lütke's framework with maximum likelihood, but in Lütke's situation, the slope is not random. When the slope becomes random on the between level, so this becomes beta 1j multiplied that within part of the covariate, you can expand this like this, and then you end up with beta 1j times xij. That's fine, but then you end up with the product of these two random effects. And whenever you actually get a product of two random effects, the log likelihood has no closed form expression, and therefore it's not possible to, you need to use numerical integration to actually compute the maximum likelihood. And numerical integration is not practical because you're going to have, if you have many covariates, with, you have too many random effects in there. So numerical integration is not practical, and that's what actually led to this hybrid model. And the hybrid model is, we have to talk about the hybrid model. This is actually Mplus default with the ML estimator. So what we do is very similar to what the uncentered model does. So we basically keep the entire X in front of the random slope on the within level. And then it's slightly better than the latent, than the uncentered model, because here on the between level, we're using the correct mean, the true mean rather than the sample mean for the between. So potentially this framework could actually resolve, Lütke's bias with random slopes. But actually it doesn't, because it's got the same problems that the uncentered method has. So it's got this strange interaction term that goes in there. and it's got other problems. It doesn't separate the effect from on the within level and the effect on the between level. So you have to apply this additional algebra. For example, Preacher in the mediation models in the 2010 paper have some of that algebra. For large clusters, nothing disappears. This interaction term that goes in there, those become super well estimated, and the interaction term stays there. So yeah, that's the Mplus uses that hybrid method as the ML estimator. You can compute also any of these other methods, centering methods, of course, using the define commands that I mentioned earlier, the center, grant mean, a group mean, and this cluster mean command that will let you actually construct the cluster mean to be used on the between level. The hybrid method also doesn't accommodate missing data, and it also it requires a lot of work to actually make proper inference. And in fact, one of the reasons we started pushing in this area, because we found an error in Preacher's article, and his actually algebra is incorrect, and the way he computes the indirect effect in the 2-on-1 mediation model, I'll show you that a little later, is incorrect. So the algebra, you have this, because we're putting the whole variable on the within level, we are making the inference more difficult to separate the within and the between. You need to do this algebraically, analytically, by yourself. And if you don't, and the more complicated the model is, the more complicated that algebra becomes, and it's impossible to disentangle the levels, and the inference becomes prohibitive basically. And so the latent centering is going to resolve that, because it cleanly separates this. It's also, one of the other problems with that, we've been frustrated, is the fact that the Mplus users actually, we were never sure whether they know what they're running, whether they know that they're actually running the hybrid model where the covariate on the within level is not centered. And that's the major source of the confusion, was that with random slopes, we do the uncentered version on the within level, but with non-random slopes, we will do the latent center version on the within level. And so and we sort of not telling them very cleanly that we're doing that, and for the user, they have to kind of figure it out. I was actually surprised that with the Preacher's article that he figured out that what we're doing actually, and to actually make an attempt to actually get to the right analytics to actually disentangle the within and the between level. Well, bottom line is, in the ML framework, there are no great options. If there were if there was a great option, we would have used it, but there are none. So also, just in version 8, the base estimator also was based on the hybrid method. And we've now, in version 8.1, we've now switched to the latent centering. And here's what the latent centering, of course, by now you should have already known what's going to happen. We decompose the covariate as a within and the between. On the within level, we've got the random slope here and the random intercept, and we are only using the within portion of that variable. And so we have a clean separation. This is just the within portion, and then on the between portion, this is just the stuff that's between level. Yeah, there was one algorithmic change that we were supposed to get this done to actually estimate this. Is basically we cannot estimate with this. We cannot estimate all the random effects at the same time like we used to do, and now we have to estimate them in 2 separate steps. So we can actually split the ones. Beta 1 is separated here with alpha j and bj, and that actually eliminates the problem with the product of 2 random effects. This model can accommodate missing data. It cleanly separates the within and the between effects. It's a little more complex to estimate, but not so. In case it could even potentially become non-convergence, but and in that case, you can of course use any of the other methods. But we have not seen any major drawbacks of actually switching forever for this method, and it was one of the last changes actually that we decided to do just before releasing 8.1. We decided we're going to go for it full all the way with this, and actually have this as a default now with base. So and embrace it, basically, is what we decided to do. We're gonna stick with it, and we see that it's the right thing to do. I'll show you the simulation. You know, it's very, there's no doubt. Any number of covariates, random effects. Mediation models that were previously intractable, very simple now. Just a simple simulation. First, we start with a very simple model of two-level regression, and we are going to have random intercept, random slope, and also because of the between part of the x, we have three random coefficients here, and we are going to compare the observed and the latent centering, and here the results of the simulation study. So you can see the latent centering, no bias anywhere, perfect coverage. The observed centering shows that. So there's basically, in this model here, it's just a straight regression. We don't have any model on the between level. It's all the effects are, random slopes are just unstructured. So here the results, again, the observed centering shows the bias in the variance covariance structures, in the variance covariance of the random effects, and some of the residual on the within level. The uncentered and the hybrid method, again, you need the major algebra there to go back to the original scale, the generating scale that separates the levels. So that's why the biases are so huge over here. The observed centering biases, they disappear when you have cluster sizes of 100 or more. But the bottom line is latent centering works, solves all these biases. Let's look now at a simulation study for the contextual effect. So this is basically, this model is very similar to Lütke's model, except we've added now this random slope. So we're going to study the contextual effect, the difference between, we have two variables, x and y. We have one effect on the within level, one on the between level, and we want to know the difference. Basically, we're most interested in the fact that there's a difference between these two coefficients. So this is basically Lütke's model. What we added here is the random slope instead of a fixed slope on the within level. And we also added, now that we have the random slope, we also added we added this xb to predict that random slope as well, the way it predicts the random intercept. So let's see the simulation results for this case. Latent centering works great, coverage and almost no bias. Observed centering, biases everywhere, coverage is poor everywhere. There's virtually like this one parameter, two parameters out of the whole set of parameters here that don't have bias and have good coverage. So latent centering can solve contextual effect biases even with random slope in the base framework. And then Lütke's bias as a term is essentially a misnomer in this particular example. As you can see, the bias doesn't occur just for the contextual effect, it's everywhere. Every parameter gets it. Okay, let's look at now just the B2 parameter in these same settings. Basically, that's the between level effect of the X on Y. With the latent and observed centering, that's basically simply the parameter beta 2. With the ground centering, you've got, you have to use a, algebra to figure out what it is in the original scale where that separates the level. So it's beta 1 plus beta 2. With the uncentered and the hybrid method, you get even more complicated formula. So it's that, but fairly simple still. And here the results. Estimate for the latent centering, the beta 2 is actually the quantity, the original quantity was 1. So you can see pretty much all of them have bias. The hybrid method decreased the bias of the observed centering and the uncentered. Let's see, what else do we see here? Look at the mean square there. It's almost, with the hybrid method, it's 2.5 times greater. With the observed centering, it's almost twice bigger. So here are the conclusions. It's not just bias. So the observed centering also shows the standard error underestimation by almost a factor of 2. And that's why you get the low coverage with the observed centering. The precision, in terms of precision, is just destroying, the latent centering is destroying the other options. And this is, just for the hybrid method. It's difficult to recommend because, okay, well, it reduced the bias a little bit, but look at the price that it paid for it. Is the mean square there are substantially larger. Let's look at now what happens in the probit model. Can we do this in probit model? Same thing. We can do it in probit model as well. So we've got, y is categorical, x is continuous. We have the same situation, random intercept, random slope. The covariate is split as a within between, with proper separation of the levels. And this is a new feature in Mplus. It's everything here is based on cluster-specific polychloric correlation, which we've never had before. Without random slope, you can do this model, of course, with version 8 with base and also with WSMV. That's the same model we have in WSMV. You can do that in there as well. With random slopes, it's only possible in version 8.1. And here are the results. When we generate with contextual effect, so this is Lütke's bias. Lütke's bias is has that specific feature that it does not, it becomes zero. Lütke's bias becomes zero if the data really doesn't have contextual effect. And same thing we see here in the multi-level probit model. If the data doesn't have contextual effect, then there's no bias with the observed centering. If the data has contextual effect, the bias is substantial. And I'm putting this now, instead of looking at beta 2, I look at the correlation. The correlation, that's a little more easier to understand. The correlation between these two random effects. So this is on correlation scale, so you can appreciate the bias, what we're talking about. And anyway, so when you have contextual effect, observed centering again leads to bias. And that also happens in multi-level probit. Multi-level probit with and without random slopes. So next we're going to, so I showed you before y was binary, x was continuous. Now we're going to switch. Y is going to be continuous, x is going to be binary. And in this case, we can do the same thing. We can we're going to have to involve now a little bit more the underlying continuous variable x star. That's basically being cut to obtain x, and that x star is the one that gets the decomposition as a within and between. And on the within level, we have the same stuff that we had before with random intercept, random slope, but now we're going to use the within portion of the underlying continuous variable x star. And on the between level, we use the x star between. So this is the model when we have a binary predictor in a multi-level model. Binary predictor in a multi-level model. And, what we are trying, this is going to be the toughest portion of this that, it's going to convince, it's going to take a long time to convince people that this is the right thing to do. Because you have a simple predictor like gender, for example. Why would you actually want to actually switch this from the observed scale to make that predictor on the latent scale? And I'll give you here the 4 reasons I will show you. So the main one is why would you switch from the observed to the latent scale for a categorical predictor? So the first one is if the distribution of X is not invariant across cluster. Now, with the gender example, very often that is invariant. If you have like classrooms and students within classrooms, that is invariant. So this doesn't qualify for that. But if you actually look at gender and companies' board directors, you know that actually is not invariant across clusters. And so anyway, so if the binary variable is not invariant across clusters, that already is a dependent variable. So it's being affected by the cluster variable. And if it's being affected by the cluster variable, then you better model it, because otherwise you get a model misspecification. If it's a dependent variable, and it is a dependent variable because there's another variable that's affecting it, is the clustering, The best way to model a binary variable in two-level model as a dependent variable is through the probit model, and using this latent scale. So basically, once you get the probit model in there, then that means you're using the latent scale. Second reason is if you have missing data on the binary predictor, that requires full modeling. And again, you're going to the best way to do it is through the probit model. The third reason is that the predictor is a mediator. If that variable itself is predicted by another variable, then again you will need full modeling of the binary variable and use the probit model and latent scale. And finally, if you're trying to do contextual effect studying, I would just point out that there's a major problem with the observed centering, is the fact that within and between level are not independent anymore. So in general, what we were doing with the observed centering when it was continuous predictor, when you center the within and the between, they become independent. And so that allows you to actually, that the levels become independent. And so that allows you to actually study these within level effects and between level effects, cleanly separate them. But you can't do this with binary variables because the mean of the binary variable in the cluster determines the variance on the within level. If the mean is a probability P, right, that's the probability P, then you get that the variance on the within level is P times 1 minus P. So the within and the between level are not independent. You can't make them independent. You can't separate the within and the between effects. And that's another reason that we think that, you really need to, cleanly go to the latent scale. So here are the results of this simulation study. Again, this is a binary predictor. Continuous dependent variable. And, with contextual effect, you can see the observed centering leads to quite large biases. When you take the contextual effect out, the bias doesn't disappear in this case. Also, you can see that as the cluster size increases, that observed centering bias tends to decrease. So it behaves exactly like Lütke's bias. So it is Lütke's bias again in this case as well. However, there is another bias here. This bias over here, where we took the contextual effect out, doesn't decrease sample size. No, it's not going away. And that one is basically due to the link function and basically the censoring that occurs on the probability scale that truncates the correlation. When you truncate a variable, you always truncate the correlation. So this is sort of related to the ICC. This bias actually depends on the ICC of the x, and the larger the ICC of the x is, the bigger that bias will be. So that's additional bias that we sort of call it the bias due to the nonlinearity of the link function. That also comes in there. Same thing with random slopes. You can get the same. Again, you can estimate. If you redo this simulation study with random slopes, again, you see Lütke's bias here. When there's contextual effect, you get bias estimates even if you use the observed centering, and the latent centering resolves that bias as well. All right, so finally we're getting to time series models, and the two separate the first thing you need to understand that the two separate concepts when you talk about time series models. So you have the contemporaneous centering, and that contemporaneous centering applies for centering the predictor, a predictor from the same time period, and that is Lütke's bias. When you use observed centering, that produces Lütke's bias. But there's a separate issue, which is basically the predictor, which is a lagged predictor. So it can be the same, it's this variable and it's the same variable, but from a different period. And how do you center that predictor? In an autoregressive model, you regress the variable in itself from a different period. So how do you center that predictor? And if you use observed centering there, then you get Nikiel's bias. So this is the difference between the two different biases in there. What's available, here's what's available basically in DSEM in version 8.1, both lag and contemporaneous latent centering is available for both continuous and categorical, and both for random and non-random slopes. So basically we've covered everything within DSEM. Within our DSEM, first of all, we don't have the categorical stuff, and so for the continuous case, we have everything. So lagged and contemporaneous and random and non-random slopes. For categoricals, we have some models, so it's difficult to actually define exactly when you can use. You can only do contemporaneous centering for categorical in RDSM, and it's not even always, but both for random and non-random slopes. So this is what's coming out now. And I'll just point out that I've seen already 2 applications of this, so the contemporaneous continuous latent centering by Hammaker in the DSEM framework, and then Bengt has a similar application in RDSEM. So just a quick review of what the Nichols bias model. So this is the mean for the individual I, and this is basically the deviation away from the mean at time point t, and this process is autoregressive with a random autoregressive coefficient of phi. And the Nichols bias occurs when this predictor is actually centered. Instead of the true mean, we use the sample mean, and that Nichols bias is in the that parameter phi, which is the expected value of the random autoregressive coefficient. And basically that Nichols bias formula is right here, and that disappears when you have large time series. As you can see, t is in the denominator, so it will disappear when you have t greater than 100. It will be very small. And the source of the bias is again the same thing, where you're using basically the sample mean without accounting for the error in the sample mean, right? The measurement error in the sample mean, and this bias is resolved with latent centering in version 8. So the new thing that we bring in here is that the same kind of you can do the same categorical, the same kind of modeling for categorical data. So just a little example. So y will be binary, and we're going to use y star for the underlying continuous variable, and the autoregressive process is going to be on the y star, exactly the same way as in the previous slide for the continuous case. And this phi is now going to be a random tetrachloric autocorrelation, and we're going to see what happens to if this Nichols bias can be found here as well. So this is a new model in version 8.1, and that offers a time series models for categorical variables. In version 8, we had some models for categorical variables, but they required latent variables behind them to create and then that latent variable itself will have the autoregressive process. And those models actually were quite problematic, and indeed, this is why we actually decided to go into creating these autoregressive models directly for the categorical variable itself rather than for the latent variable. Because these models were slow, they required large amount of samples, and this is why we chose this project. And now with this model, where the autoregressive model becomes directly on the y's instead of latent variables, we have that you can use this as few as 20 time points. You can estimate these models, and no need for additional latent variable, and it's much faster to converge. Those are easy models to estimate. Within seconds, you can estimate such random tetrachloric autocorrelation models. And this is also a new concept. You can actually type this in Google and you see 0 papers. And, not quite sure why it never came before, but let's look at the smashing advantages of this. This framework actually has over Markov chain. It's even uncomparable. It's so much better. So first of all, you can get lags greater than 1. Second, you cannot easily covariates. Third, you can fit this in multi-level DSEM, very easily. You still get random transition probabilities also through this random tetrachloric autocorrelation. It can be used with categorical variables with more than 2 categories, and look what happens if it's also so much more parsimonious than Markov chain models. If you have a single variable with five categories, the Markov chain model would estimate 24 parameters, while this random tetrachloric correlation would estimate essentially five parameters, because you don't have to model the full distribution. It's just one correlation between the two. And if you have 2 variables, if you make the bivariate model, then the Markov chain model is going to have 625 parameters, and the tetrachloric correlation is going to have 13. So the difference becomes even more dramatic when you talk about multivariate models. Let's look at the results. So we estimated this with several different methods here. I'm actually not going to skip this but you can see again that latent centering doesn't have any bias. The observed centering shows bias, and that bias does not disappear here. Like in the continuous case, Nikel's bias disappeared as the cluster sizes increase, but that doesn't disappear. The uncentered method also doesn't fix. This bivariate centered method actually fixes it, but this is basically also, it's not available anywhere else but in version 8.1, where you basically treat the two categorical variables instead of as being one and its lagged version. You can still use the that variable and just treat the lagged version as a separate variable. That's also done quite a lot in time series modeling and structure equation modeling, the combination of those two. And so that bivariate centered can actually be eliminate the bias. Here's another simulation here. You can see latent centering, perfect coverage, and no bias. Okay, so finally we got to a two-level mediation case. And this looks a little messy, but it's actually quite simple. It's a 2-1-1 two-level mediation case. So all it does here is we separate the y variable as a within and between. Then you have the mediator variable within and between. And then on the within level, you've got a random slope coefficient for between the y and m. And on the between level, so the fact that there's 2 here, 2, 1, 1, that means that the x variable is on level 2 only. And so basically we have x is a between cluster level variable, and here's on the between level is basically y is regressed on the mediator and the covariate, and the mediator on the covariate. That's just a little mediator model. The important thing here is that, again, we've got this random slope in front of the mediator on the within level. And here's Pritchard's article. And just to point out that that's a very prominently visible article. It's got over 1,000 citations already from 2010. And it's based on that hybrid model centering method, which basically, instead of using the within part over here, would actually use the entire thing. And that Pritchard actually figured out that you can compute the correct indirect effect by simply using this formula, beta 1 plus beta 2 times beta 4. While the latent centering, if you estimate through the latent centering, it's very easy. It's beta 2 times beta 4. In latent centering, you cleanly separate the within and the between. And because the between becomes like a single level model, just a separate group, you can actually just do the regular thing. The indirect effect is basically the product of this and this, the beta 2 and beta 4. So here are the results. So let's see what I want to point out. First of all, I want to point out that the hybrid method this is basically what happens for large sample sizes. The hybrid method has got this substantially large mean square there, much larger than the observed and the latent centering. So we've got this problem that we discovered now. The second problem is, of course, again, when you have contextual effect between the y and the m, you've got the observed centering, it's got these huge biases that it's going to show. And look at the mean square there. It's almost doubles, in these cases here between the latent and the observed centering, and mostly because of the bias. So anyway, the latent centering is better than both of these. I want to also bring in this article by McNish, that's 2017. Unfortunately, we found many errors in that article, and he concluded that the observed centering is best. He accidentally generated data only without contextual effect. So he basically saw these rows where that says no. And you can see that if you look only at these rows, then there's not much. And, again, this is based on, this latent, the Lütke's bias, because only it happens when there's no contextual effect. The Lütke's bias actually will happen only when there is contextual effect. So if you only generate data without the contextual effect, of course you won't see it. So there's that error that is in McNish's article, and he missed that, but there's more than that. There's many errors in there, unfortunately. We've been trying to communicate and point this out, but basically he did exactly this simulation and his results are completely different for some reason. So the next thing is another error that we found is the fact that Preacher's formula actually doesn't apply if you slightly modify that model. So if you actually, random effects can be correlated, right? So if you actually introduce a correlation between the random slope and the random intercept for M, you introduce this parameter rho here, then Preacher's formula no longer holds. And you can use the potential outcome methodology to actually compute the correct indirect effect formula, and it's this formula. And we conducted a little simulation study to actually show you that indeed Preacher's formula is no longer correct. And so here's the latent centering method. This is, again, the latent formula is very simple, beta 2 times beta 4. Here's what Preacher formula is for the indirect effect, and here's what the true formula is really with the hybrid method, using the potential outcome to compute it. And you can see the bias is 0 for this, for the correct formula, and for the latent, and the bias is substantial if you use Preacher's formula. So coverage 0 here, and huge mean square there comparison. Nevertheless, so this we did that. We didn't do. The problem is, like, Planck sort of got a little excited on how do we do this in general. You know, you can't do this in general. Don't try this at home is basically the conclusion about this hybrid method. You don't want to. It's too complicated. It's not worth it. The latent centering is the answer here. And look at the mean square there, 1/3, even if you fix the formula. Final simulation here again in this 2-on-1 mediation example, and we generate data as MAR using this formula and MCAR using this formula. And we eliminate the contextual effects here, so we generate data without contextual effect to make sure that Lütke's bias doesn't go in there. And when you have missing data on the mediator, you have to, you can still perform this kind of observed centering. Of course, you're going to have to just use the average of the observed values, but that of course will have problems. Anyway, here are the results of this final simulation. Latent centering solves that bias, and there's this bias that exists basically with virtually every other method you try with the observed centering. So, I'm going to stop here and see if there's any questions.
I have a question. Can you hear me?
Yeah.
Okay, so I was wondering about, so is latent centering option only available with the Bayes estimator?
It is, yeah. It's not possible. It's just not possible with anything else. With ML, it's not possible. Okay, hold on 1 second. So the latent centering option is there already when you have non-random slope. It only becomes an issue, when it's with random slopes. And in that case, the latent centering will only be available in the Bayes framework, and that's not going to change. We can't do anything about it. It's not computationally feasible.
Okay. So if I have about 40 time points, what kind of power do you need for DSEM or RDSEM? Is 40 too small for?
No, that's not too small. I'll refer you to that paper by Bengt and Martin that came in the Structure Equation Model Journal just in the very last issue. There's a paper on the power of DSEM.
It's on our website also.
Yeah, with the very last issue of the Structure Equation Journal. Yeah.
Okay. Thank you.
Yeah.
I wanted to say that if you do applications of these techniques, we're really interested in seeing your papers, and we'll post them on our website just to help others learn the ropes here, because it's all very new.
Can I just toss this out? So, if you noticed that when I talked about this interaction term that everybody hates, that it's there, I claimed that, if you actually start collecting real data, that, that this is always, and we used like a DIC or BIC to compare the models, you're always going to reject it. There's no case where this is justifiable, and we can actually see it in real data that it doesn't work. Then we tried the first data set, and then it actually DIC ended up going the other wrong way. But it would be interesting to collect more data set. In certain situations, of course, you can have that interaction term be needed, and maybe that coefficient, the fact that it's fixed to 1, it's maybe not that important. So maybe it's indeed. But it would be nice to actually start collecting real data sets and actually get after this stuff in a more consistent way.
And again, one of the papers that TMR is putting together is showing examples with RDSEM and DSEM input for different cases. That'll be helpful too.
So I can say one more thing about RDSEM. RDSEM is so much simpler to understand. It looks actually more complicated, but actually it's simpler to understand.
Okay, we are all shocked. Amazing work. Anyway, thank you so much, Tiomir. Thanks, Bengt.
All right.
It's already 11:32, so I think we will have to close it here. But if there are questions from the audience, please email Tiomir, Bengt, and me, and Katya, so we can continue this conversation. Thank you so much.
All right. Thank you. Thanks.
Thank you.